So, what are the things we have discussed till now? We have discussed what are the needs of a thermal management system, what are the function of a thermal management system. We have also tried to understand what would be the optimum temperature for a cell to get the maximum cycle life of the thermal management system. Then we studied the various modes of thermal management system. We try to understand the heat load calculations, and then we have done active thermal management system. Then we also understand one curve which is collection of the various mode which we can utilize based upon the heat transfer coefficient calculation in the active thermal management system or passive thermal management system. Let us understand now passive thermal management. Heat sinks, it is one of the simplest and most widely used passive thermal management system, especially on electronics. The good thing about electronics, the most of the temperature range is around 70 degree plus. However, our ambient goes maximum 45 plus, 45-50 degree, nothing more than that. So, you always have a temperature differential possible or temperature gradient possible, and in such cases heat sinks works well if properly designed, properly selected. However, it can take very low heat flux 0.05 watt per centimeter square, but easiest and cheapest to implement and maintain, since you do not have anything active, it is just a part. Reliability is very good. The only problem is that the heat flux is very low, which you can remove through this. The next comes heat pipe. Again, when I say heat pipe, it could be used as a passive thermal management system as well as with the active thermal management system using air cooling. The good thing about heat pipe cooling is the thermal conductivity is 10 to 100 times of the copper. And how does that happen? Because of the partial vapor inside this pipes. It could be water, it could be something else. The pressure is, some vacuum is created, so your partial pressure of the water or whatever you say, vapor pressure comes down and it can convert into vapor at very low temperature. So, one end is evaporator, other end is condenser. So, evaporator it takes heat, condenser it rejects heat. So, rejection of heat can be using the fins or fins plus air cooling or fins plus any other mode. It can take heat flux of 5 watt to 750 watts per meter square, per centimeter square. So, if you see from here, it has almost 100 times more, and here it is much more than 100 times, it is almost 10,000 times. But when you are trying to achieve this system, then you have to go for again the active cooling system, air cooled or water cooled. However, lower end can be achieved using the passive thermal management system, like just have a good amount of fins exposed to the ambient air. In that way you can utilize this one. Thermal interface materials. What happens whenever you are attaching two surfaces, like in electrical contact resistance, we also have a thermal contact resistance, and to reduce those thermal contact resistance, we use different types of material which will have generally good thermal conductivity up to 3 watt per meter square per Kelvin, and then we glue second part, like if I have to use heat sink between these two surfaces, there is a possibility of air entrapment in between that, there is a possibility of that there is not very good contact. So, you utilize this type of thermal interface material, so that I should have a maximum contact, and when I have a maximum contact, that leads to more heat transfer, more surface area. And generally these materials are all, and whenever we want to isolate or insulate electrical conductive material from other system, at those places also we use this type of thermal interface material, which have a good thermal conductivity, but very bad electrical conductor. Phase change materials like PCM. And when we say phase change material, that means it changes its phase either from vapor to liquid, liquid to vapor, or liquid to solid, solid to liquid, and there are many phase change material which can go from vapor to solid, solid to vapor also. So, the heat absorption is generally done by phase change, and you know the order of heat transfer coefficient. If there is a phase change, it could be hundreds times more than through the regular convection, either forced or natural, by virtue of its phase change. Wide temperature range, something between -30 to 150 degree centigrade. However, you have to be very careful in selecting the phase change material, especially for the battery cooling system. You have to see what is your ambient condition, and based upon that only you should select a phase change material. Otherwise, it will not work as intended. So, if my temperature ambient condition is 45 degree, I would like to have a phase change material something more than 45 degree, but I do not want to go too high. So, maybe around 50 degree centigrade. The drawback of phase change materials are generally it also act like a thermal insulator. So, to enhance the heat transfer coefficient or to enhance the heat transfer capacity, several ways we work out. One of them using the finned surface within your pack, nano conductive materials, thermal conductive materials, or wire mesh, so that my thermal conductivity should also increase and I should be able to utilize the most of the latent heat capacity of the phase change material. Otherwise, only the nearby surfaces gets melted and heat cannot get transferred to the outer layer because of the very low thermal conductivity. To improve that, we try to use wire mesh, finned surface, nano particles, high thermal conductivity nanoparticles mixed with the phase change material. So, let us calculate, since phase change materials are most widely used thermal management system in battery packs for passive thermal management. So, let us do an example on that. Before going to the example, we should understand how does it works out. So, there would be initial sensible heating of the solid. In that case, the temperature will rise. Then at particular temperature, it will start changing its phase, and that from solid to liquid, what we say is latent heat of fusion. And you see, our temperature does not change here, but it can take a huge amount of the heat. Then again, it is a sensible heating, temperature start rising up. and then now liquid start converting into the vapor. Again it can take a huge heat because of it, we say it's a latent heat capacity. Now once it is vapor, now it started superheating, again the sensible heating start. So sensible heating, latent heat. What we use in natural convection or in forced convection is the sensible heating or cooling. We are using the phase change material, what we do? We are using the latent heat plus a part of sensible heat, but most of the energy comes from the latent heat or latent cooling. So we are already working with 2P16S battery pack. That packs rejects 62.72 watt. Now if the pack is discharged at 1C rate from 60% to 0%, evaluate the PCM mass required to maintain and regulate the pack temperature at 45 degrees centigrade. So how much we have? At 1C discharge we already know it is 60.72 watt, and now we are discharging from 60% to 0%. The PCM specification has been given. The material is paraffin, melting temperature 41 degrees centigrade, latent heat capacity is 294.9 kilojoule per kg, the density is 733 kg per meter cube. What is energy to be absorbed by PCM? 62.72 into 0.6 hour I have taken here, multiplied with the second, because considering the linear relationship, generally it is not so linear, but let us assume for simplicity it is a linear relationship 60% to 0%. So we need to absorb 135.47 kilojoule heat. Now what would be the mass of PCM required? 1 kg can take 294.9 kilojoule. So you just divide this by this. So around 460 grams PCM we required. The good thing about this is that my ambient condition, if you see the last problem, my ambient condition is 35 degree. This PCM starts melting at 41 degrees C. Generally the PCM does not have any rigid melting points. It would be something like, now this PCM will start melting between 41 to 45 degrees C, and that would come in the data sheet, a range of the temperature in which start working well. So my battery temperature will never go more than 45 degrees centigrade if I am discharging from 60% to 0%, but if it is from 100% to 0%, then what it would have been the case? What would have been the weight if I would have been discharging from 60% to 0%, sorry 100% to 0%. So this is for 60%, around 460 gram. For 100% to 0%, it could have been something like around 800 gram. And when we discharge, we always discharge from 100% to 0% if you remove the DOD. So to make this pack where my ambient temperature never exceeds more than 35 degree. In such cases, if I use 800 gram PCM, it is not just PCM. Now I have to design in such a way that the PCM keeps on melting as soon as heat is getting generated. That means the heat generated by battery pack should be felt by PCM. We can use wire mesh, we can use fins, or we can use very thin layers of PCM, because the thermal conductivity of PCMs are generally very, very low. Okay, so we will move to next, materials and design. The thermal management system materials are basically selected based upon thermal, mechanical and electrical properties. cost and manufacturing constraints. Now, let us come back to thermal properties. The coefficient of thermal expansion, if that is very high, what will happen? Thermal expansion, if you apply temperature, it will start expanding. What we want? Very low thermal expansion coefficient, because otherwise what will happen? There is a possibility of developing very high thermal stress, and that could lead to the mechanical failure, leakage, all the things. It can cause non-homogeneous deformation. Wherever the stress is more, it will deform more there. Wherever stress is less, it will deform less there. Thermal conductivities. We were discussing in phase change material, it basically acts as an insulator. So, what type of material we require? We require a material which should have a high thermal conductivity, because what we want to generally transfer the heat from cell to the ambient, and any such medium, if it has very high thermal conductivity, it is much easy, but there is a drawback also. It can also gain the heat from the ambient. So, you have to be careful in selecting that. But within the cells or within the battery pack, we always prefer high thermal conductive material. Reason is, it helps in maintaining the temperature uniformity across the pack. When it happens, the differential degradation because of the differential temperature does not take place. So, when structure is required to be insensitive to spatial thermal, spatial, that means between the cells or between the modules, then high lambda by alpha ratio, that means alpha by, so when I say high, so lambda is very supposed to be high, alpha supposed to be very low. Now, other than that, there is a during the dynamic disturbance, you also have to worry is specific heat capacity. We have talked a lot of material, you know, water has the best specific heat capacity. The only problem with water is that it is a corrosive, and then it is not electrical insulator. So, we always try to prefer high thermal capacity. So, when we have a high thermal capacity, the change of temperature is very slow. That is what is second point, absorb more energy before showing significant temperature changes. It is a capacity which it can take heat or can reject heat. Then there is something known as thermal diffusivity, and it is nothing but lambda by rho Cp. And what it says, how fast thermal propagation or thermal disturbance can propagate in any medium. So, these four parameters, alpha, lambda, Cp and thermal diffusivity becomes important, because the battery pack in principle is of transient. Any thermal management in the battery pack by virtue of it is generally in dynamic in nature or transient in nature. And then material selection, when we say we take care of all thermal, mechanical as well as electrical properties. Then cost as well as manufacturing. We use various type of material in battery pack components. External casing like metal, aluminum, steels, plastic, ABS, PC, composites, CRPF, armored Kevlar. Cells and modules holders generally is metal. In metals, if you select, then aluminum with insulation, so that I should have high thermal conductivity but no electrical conductivity. And the plastic like ABS, and polycarbonate. Bus bar interconnects generally made of copper, aluminum, nickel, and the thermal management system, when we say the cold plates are generally made of aluminum, heat pipes are generally copper, coolant tubes are generally made of aluminum, ABS, EPDF, etc. Now thermal insulation. Till now what we are talking about thermal conductivity, but thermal insulation also become important when I don't want something to propagate between cells. Like if somehow one cell has got heated up and going towards thermal runaway. A thermal runaway is a situation where lot of energy get released very quickly. In such cases, I don't want the thermal energy to move to the next cell, and that's where we require something known as thermal insulation. Better the thermal insulation, lesser the movement of thermal energy from one cell to other cells, and that helps to mitigate the situation of extreme situation like thermal runaway. Whenever we say thermal insulation, it should be it should have a very poor thermal conductivity, less than air. Air has a thermal conductivity of 0.026 watt per meter per Kelvin. They provide very good insulation when they are in compact form. If they are not in contact, air itself is a very good insulator. But what we want to provide a good thermal insulation when they are in compact form. This thermal insulation also helps to reduce the ambient condition. If I provide the proper good thermal insulation on the pack, I have to just worry about what is the heat generation in the pack. I don't have to worry the higher temperature or lower temperature of ambient condition, because the heat will not get penetrated, or road condition. Cell to cell insulation can also prevent a spreading of thermal runaway from one cell to other cells, because it does not allow the heat to penetrate to other cell, and if it does not, then other cell will be safe. Only one cell, instead of having whole battery pack into cascading effect because of one cell thermal runaway, it restricts the thermal runaway to that particular cells only. Various material we use, mineral wools to the porous materials. Ultra thin has a very good capacity here. Generally, these mineral wools are not used between cell to cell level. However, it can be used as a pack insulation. Thanks. What are the things we monitor in a battery pack? What are the thermal parameters generally we monitor in the battery pack? So what we monitor in a battery pack is basically temperature, and rest of the things we calculate from that what could happen. So we'll come back to the BMS when we'll go for BMS, but what are the things we need to do? Overheat protection. BMS should cut off. If I'm measuring a temperature, then after a particular temperature, the BMS will cut off. But what we are measuring is a temperature. Optimized current, again what we are measuring is a temperature. So that beyond some particular temperature, wherever my material is getting failed or can be failed through experiment or through calculation, we find out those situations. Uniform heat distribution or uniform temperature, because that helps in maintaining the battery pack for higher number of cycles. So I don't want to have differential temperature in between the battery pack. force cooling system if I am utilizing. So, based upon temperature feedback, it should switch on or modulate. And if you see in a battery pack, there are several locations we provide the temperature sensors on BMS, for ambient temperature, on the cell surfaces. The various temperature sensors what we use in a battery pack is thermocouple, RTD, PT RTD, NI RTD and thermistor. Because of the low cost and the high reliability, thermistors are widely used as a temperature sensor in a battery pack. There are several non-contact type of sensors like IR or optical measurement sensors are also nowadays being used because of its again reliability and the accuracy, and the using the one sensor or two sensor measuring the whole pack various temperature range. So, that is also being used nowadays in various battery packs, but it is a costly. The cost may come down tomorrow if it is being started mass manufactured, but at present we are using mostly NTC type thermistor because of its low cost and high reliability. Any question till now?